The ocean goes dark in layers. Sunlight thins to a weak blue haze, then vanishes entirely, leaving a world defined by pressure, tons of it, stacked invisibly overhead. Here, a fin stroke is expensive. A heartbeat is a negotiation. Every molecule of scent, every vibration in the water matters more than sight. And yet, moving through this blackness are sharks, animals we think we recognize, made unfamiliar by the deep. Their bodies don't read like the streamlined silhouettes of coastal predators. Some glow, some drift as if time itself is thicker down here. Some carry faces that look unfinished, or jaws that fire forward like sprung machinery. Even their life histories break our expectations, growing slowly, maturing late, surviving on scraps, enduring cold that would stall most vertebrate metabolism. Today, we're diving into why nothing about deep sea sharks is normal, and why normal might be the wrong word to use in a habitat that rewrites the rules of being alive. Down here, evolution doesn't polish creatures into a single ideal shape. It improvises, compromises, and weaponizes physics, turning darkness into camouflage, scarcity into strategy, and time into a kind of shelter. The first shock is that in the deep sea, hiding can require light. At mid-water depths, there is often no seafloor to press against, no kelp forest to vanish into, no reef shadow to tuck beneath. There is only open water and a dim, ancient kind of visibility, the faint glow from above, filtering down like diluted starlight. A predator below looks up, and anything that blocks that glow becomes a silhouette, an easy target. In that geometry of danger, the underside of an animal is a liability. Many deep-sea species solve it with counter-illumination. They produce light on their bellies to erase their shadow, matching the brightness of the water above as precisely as possible. Sharks, cartilaginous fish with a lineage older than dinosaurs, are not supposed to be bioluminescent in our popular imagination. But in the lantern sharks, they are. Their skin carries photophores, tiny light organs dense enough to form glowing fields when viewed at a distance. In the velvet belly lantern shark, Etmopterus spinax, those photophores are not simply on or off like a flashlight. They are regulated by hormones, using a mechanism likened to an iris, pigment cells shifting to reveal or conceal the luminous photosites beneath. It's a biological dimmer switch, or built from the same basic cellular machinery that shallow water sharks use for color change, repurposed into a light control system for the deep. In the language of evolution, it's not invention from nothing. It's a retooling of what already exists, made useful under new constraints. That matters because it hints at how strange traits arise. Bioluminescence doesn't leave fossils. We can't dig up a glowing shark skin from the Cretaceous and point to the moment light appeared. But we can watch living systems and infer pathways. How a pigment-based camouflage response in shallow water could become luminous camouflage in darkness. The deep sea is a selective environment that rewards any edge in detection and concealment, and it does so relentlessly, generation after generation. They're in a habitat where even day and night are concepts that arrive only as chemical or behavioral rhythms. And it isn't just lantern sharks that treat light as a survival tool. Even in another small predator, the cookie cutter shark, bioluminescence becomes deception. The cookie cutter's underside glows from a network of photophores, but around its throat it carries a darker collar, a band that breaks the glow. From below, that pattern can resemble the silhouette of a small fish against faint, downwelling light, an illusion that may entice larger animals into range. Then the shark clamps on with specialized suction-like lips and a set of teeth designed for precision damage. Small upper teeth that help it anchor, and larger triangular lower teeth that act like blades. It bites, rotates its body. Ormond removes a neat plug of flesh, round as if cut by a tool. It is not a pursuit predator. It is an ectoparasite of giants, leaving signature craters in tuna, billfish, sharks, and marine mammals. It even bites things that are not food in any normal sense. Rubber sonar domes and equipment, mistakes that still speak to its feeding program. Attach, slice, twist. In the shallows, shark success often looks like speed, agility, and overwhelming force. In the deep, success can look like a small mouth with surgical teeth, a glowing belly that lies, and a body built to take only what it needs from animals too large to fight. Then, there is the second shock. Deep-sea sharks can treat time as a resource. In cold water, chemistry slows. The movement of molecules becomes less frantic, and metabolism, the pace of living, can drop with it. For some species, that slowing is not merely a physiological side effect. It becomes a life strategy. Nowhere is that more startling than in the Greenland shark, Somniosus microcephalus, a predator of Arctic and North Atlantic waters that can descend into deep darkness, where temperatures hover near freezing. For decades, its age was an argument without proof. Many fish can be aged by counting growth bands in hard structures like otoliths or fin spines. But Greenland sharks don't offer those easy records. Their vertebrae are too soft to preserve clear annual rings. The breakthrough came from an unexpected place: the eye. In the center of the lens are proteins formed before birth, metabolically inert afterward, biological time capsules. By radiocarbon dating these lens proteins, researchers could estimate age, and the results were staggering. The largest individuals examined were estimated in the range of centuries, with one large female estimated between roughly 272 and 512 years old. The method carries uncertainty. Radiocarbon dating provides ranges rather than a single number, and scientists continue refining the estimates. But even the conservative end makes the Greenland shark the longest-lived vertebrate known. A lifespan like that forces different questions. In most animals, death arrives as a trade-off. Grow fast, reproduce early, burn bright, and accept wear. In Greenland sharks, the pace is the opposite. They grow slowly, less than a centimeter a year in some estimates, and may not reach sexual maturity until well past a century. They swim with a kind of patience that seems less like laziness and more like economy. Even their top speed is low compared to many fish their size. This is not immortality. It is a different bargain with the environment. In the deep and the cold, food can be unpredictable. The cost of motion is high. The Greenland shark's slow metabolism may be part of how it stretches energy across decades, then centuries. An ecological strategy that makes sense in a world where meals may come as episodic windfalls, a carcass sinking from above, a fish caught in a moment of opportunity, an animal weakened by winter. And yet, this strangeness has a shadow. A species that matures over a century cannot quickly replace itself. The deep sea often feels untouched, but it is not beyond human reach. Long lines and nets set for other fish can catch Greenland sharks as bycatch, removing animals that represent not merely individuals, but time, entire lifetimes of slow growth. Conservation in the deep is complicated because the deep is hard to monitor, but The biological math is unforgiving. When life histories stretch out, recovery times stretch out too. If the Greenland shark teaches that time can be a survival adaptation, the goblin shark reveals something else. In the deep, you can trade speed for mechanics. The goblin shark, Mitsukurina ostoni, is often described in images as ghostly pink, its tissues showing through because it lacks strong pigmentation. But its true otherworldliness is functional, not aesthetic. It is a slow swimmer, an animal living where food is scarce, and encounters with prey may be brief and unpredictable. In that context, chasing is expensive and failing is costly. And when researchers analyzed the first at-sea footage of goblin sharks capturing prey, they documented a feeding mechanism unlike anything else in a large shark. The jaws do not merely open and close. They swing, then launch forward, projecting out from the head in a rapid strike, what the researchers termed slingshot feeding. In the documented events, the jaws projected to nearly 1/10 of the shark's body length, at a maximum velocity of about 3.1 meters per second, described as the fastest and greatest jaw protrusion among sharks. The movement is over in fractions of a second, a sudden acceleration in an animal otherwise built for slow cruising. It is, in effect, a mechanical ambush. The body approaches quietly, the jaws do the sprinting. This is how deep-sea evolution often operates. Instead of optimizing the entire animal for speed, which would demand high metabolic rates, more oxygen, more frequent feeding, it localizes performance into a specific structure at a critical moment. The goblin shark's jaw apparatus becomes a spring-loaded solution to scarcity. The research even notes oddities still unexplained, like the mouth opening and closing again during jaw retraction. Details that remind us how incomplete our understanding remains, even when we finally witness the behavior directly. And watching it, you begin to see the deep sea as a place where sensory information is fragmented. Light is limited, scent travels, but slowly and unevenly. Pressure and temperature impose boundaries. Under these conditions, the distance between encounter prey and capture prey must be minimized. The goblin shark compresses that distance into a single ballistic moment. Other deep-sea sharks solve the same problem, finding and taking food through different compromises. The cookie cutter takes pieces instead of whole prey. Lantern sharks hide in a field of self-made light, reducing predation risk while they hunt smaller animals. The Greenland shark slows life down until the environment's unpredictability becomes survivable. And then there is a final layer. The deep sea is not uniformly deep. Many sharks and other midwater animals move vertically, tracking the daily rise and fall of prey in what is called diel vertical migration. Darkness is not static. It pulses with life that ascends toward the surface at night and sinks again by day. Following that migration can expose animals to cold, low oxygen zones, conditions that would challenge physiology. In studies of blunt-nosed six-gill sharks, Hexanchus griseus, researchers document pronounced vertical movements and time spent in cold water and low oxygen conditions, including time within oxygen minimum zones, regions where dissolved oxygen is naturally depressed. These zones are expanding in parts of the world as oceans warm and stratify, but even in their natural state, they form a kind of physiological gauntlet, a corridor of scarcity, in the very gas that fuels muscle and brain. For an animal that migrates through them, the body must be tuned to tolerate hypoxia, to balance energy budgets, to keep functioning where many predators cannot. The deep sea does not just ask, "Can you hunt?" It asks, "Can you hunt here, with less oxygen in colder water for longer?" Seen together, though these sharks are not a collection of oddities, they are variations on one theme. Deep sea normal is different, because the environment is different in the most fundamental ways. Light, pressure, temperature, oxygen, and food availability. Evolution responds to those constraints, not with a single blueprint, but with a portfolio of solutions. Bioluminescence becomes camouflage and communication, controlled by hormonal pathways that echo shallow water color change. A reminder that novelty is often old biology in a new role. A mouth becomes a projectile, because sprinting with the whole body is too costly in a food-poor world. Feeding becomes theft rather than predation. A circular wound cut from a passing giant as the shark returns to darkness. And aging becomes slow, not as a miracle, but as a metabolic alignment with cold water and long gaps between meals. A life stretched over centuries, still half hidden from our measurements by the uncertainties of our tools. But the deepest reason nothing about deep sea sharks feels normal is not that they are monsters, or relics, or mistakes. It's that they show how plastic life can be when the world applies pressure, literal pressure and evolutionary pressure for millions of years without relief. They reveal that shark is not a single idea. It is a framework that can accommodate glowing skin, parasitic bites, ballistic jaws, and centuries of slow motion. And even now, in an age of satellites and global maps, we are still outsiders here. We see fragments, a camera's cone of light catching a jaw as it launches. A radiocarbon curve that turns an eye lens into an estimated birthday. A pattern of glowing dots in skin tissue under a microscope. A round wound in a tuna's flank that implies a nocturnal meeting we never witnessed. The deep sea keeps most of its transactions private. For every behavior we record, there are others unfolding beyond our instruments. Silent hunts, migrations through low oxygen layers, encounters shaped by senses we barely understand. Bioluminescence itself, so central to deep life, remains partially mysterious in sharks. How light production evolved, how signals are perceived in darkness, how often it serves camouflage versus communication, and what ecological conversations are happening in wavelengths our eyes cannot separate. So the strangeness remains? And perhaps it should. For the deep ocean is not a distant planet. It is part of Earth's living system. Yet, it still functions like a frontier of biology, where familiar animals become unfamiliar not because they break the rules, but because they obey a different set. In that darkness, normal is simply what survives. And what survives down here often looks like something we would never have designed, because it is not designed at all. It is selected, tested, and refined by hunger, by cold, by low oxygen, by the geometry of light, and by time itself. Patient forces that do not care whether an animal matches our expectations, only whether it endures.